Alright, so now we're gonna start to work on rotating the wheels. For this, I'm gonna go back in my train, inside of the wheels, and let's go over here. These are the points. I'm gonna calculate the rotation on the points. Instead of trying to copy the wheels first and then rotate the wheels, this is not really handy. What I want to do is I'm gonna calculate how much the wheels have to be rotated and put those values on the points so the wheels automatically get rotated when they are copied to the points. So to do this, I'm gonna use a trail sub here, and this trail sub, I'm gonna say not preserve original, but compute velocity. So what it's doing now, it's computing the velocity. As you can see here, v is calculated. And to let me see, okay, this for now is set to 0 because there is no animation whatsoever, but I want some animation on there because I want to when I do this position on the track, I want this to work. So I'm gonna have to animate by hand now, put some keyframes here on the position on track. So what I'm gonna do is in the beginning of the animation, I'm going to put this at let's say 10, something like that, or something in there. I'm going to say Alt middle. Why are you not working? Train. Alt click to get keyframe over here at frame 1, and then all the way to the end. I'm going to say, well, let's say I want it to be somewhere here, and I'm going to put another keyframe there. So now when I scrub through the timeline, it will go here. Okay, so now if I go to v velocity, I see that there is values here. That's because there is animation now, so there is velocity. And this velocity, I'm going to use this velocity to be able to calculate how much distance my wheels, or the points of my wheels, have traveled since the last frame. So because every frame I have to update this. Well, as you know, or I think you know, is speed, velocity, is measured in meters per second. So I don't want to know how many meters per second it is traveling. I want to know how many meters per frame it's going, because I have to update it every single frame. So in order to calculate this, I have to divide this value with the amount of frames per second that I've got. So to do this, I'm going to use a wrangle node, and this is going to be a point wrangle node. And I want to actually, instead of doing everything on x and on y and on z, I want to do everything on the velocity in total. So I want to have the length of this vector. The length of this vector, it's actually the value that I'm gonna use, and I'm gonna use this as I'm gonna decide that I'm gonna call this distance traveled. So I'm gonna make a float f at distance traveled equals v at velocity divided by $fps. $fps means frames per second, so that is, in this case, if I'm going to click here, frames per second, I am on 24 frames per second. But if you up this, if you have a different frame per second, this automatically will work. Close. So let me see. Okay, so this is giving me a warning. That's because I have not yet gotten the length of this. So first I have to say length, this one, the length of v divided by $fps. And now what I've got here is a value that's called distance traveled. So the distance traveled, if I go to frame 0, there is no distance traveled, and it goes up, and every single frame it goes, there is some distance traveled. So this means the amount of distance that is traveled in one frame in meters. So that's pretty a lot, actually. I'm going pretty fast. But okay, and you see by the end, because it's easing out, by the end it's getting less. So this is the distance traveled per frame, actually. But I don't want to have the distance traveled per frame because I want to have the total distance that has been traveled. So I don't want what's been traveling last frame. I want it to have for every single frame. But unfortunately, in subland, we are in subland now, surface operators only. There is no way to be, well, there is a way, but there used to be no way to be aware of what happened in the frame before or after me. So in order to be aware of what happened in the frame before me, before now, I have to use a solver node, and this is actually a sort of dot node, so I'm going to say a solver here. And if I put this down and I put this in here, what you see there is this brain icon over here means that it's really thinking very, very hard. But if I say right mouse, allow editing of contents, if I go in there, you will see that there is a dot network here. So we're actually using a dynamics operator, and here there's some stuff in there, some blah blah, and here there's the subsolver itself, and here we can use something to do some magic. So I'm going to say back match current definition, because now if I double click in it, I automatically get to the part where I can do some magic. Well, the magic here is not very difficult, but if you don't know what's happening here, that it might be a little bit overwhelming. What's happening here is we've got the object merge. So this is the data. Actually, the input 1 is actually this input, this one that's coming in here. So you can already see that this is up input path 0 because it's indexed 0. But this is the first input. This one over here, it already says it's the previous frame. So we want to have some data from the previous frame that will be added to the data of this frame. But we want to keep the data of this frame. So I'm going to put this one over here. And now I've got some data again. You see, if I do like this, it's a strange, I want this. And now I'm going to put a wrangle in here, and I'm going to do some mumbo jumbo here again. I'm going to make a point wrangle. And with this point wrangle, I have my current data, my current geometry as an input 0. And as input 1, I'm going to use the data from the previous frame. So what am I going to do here? Well, here I'm going to have to write down some code, some vex code that is going to make sure that the distance that I traveled, which is this value here, right, this attribute that we made, that this gets added to the distance that we already traveled in the frame before us. And if we do this every frame, this will be a cumulative distance traveled. So I can do this with some code. And what I'm going to do here is, let's see, the best way would be is add distance traveled plus equals, that's a shorter way of saying, so by the way, this was a float, float distance as distance traveled is, and then we're going to have to get the value of the previous frame. So how do we do this? Well, it is an attribute, so we can access this with the point, and then we're going to say what geometry. Well, the geometry is the one from the second input, so that's the number 1 in this case, because it's the first one would be a 0, but this is 1. Then a comma, and then we're gonna have to say what is the name of the parameter, or the one that we want. It's distance traveled here. And from what point do we want this? We want this from at ptnum. For every point there's a different value, of course. So well, yeah, of course, because there's some difference in there. So what we've got now is distance traveled here is added to, or the distance traveled of the previous frame is added to the distance traveled of this frame. I'm actually going to write this different than this, because the plus is a short way of saying this, but for later I will show you that it might result in trouble. So I'm going to write this differently. I'm going to actually say is this plus this. it ends up being the same. But trust me, in a later session, in a later part of this video, I will explain why I did this way, because what I want here is what I've had so far from the previous frame, and I just want to add what I've got in the last frame. So this is what I've got here. And if I go here now, and I'm going to have a look on, on this one, go back to frame 1, distance traveled. So now if I go up, so you see that my distance travel is growing, and it never gets lower because it animates over there from here to there. You know, instead of doing this later in a later video, I'm going to do this straight away. So yeah, just improvise, Rudy, you can do this. The problem that I noticed earlier on is that once I have animation, for now I've got an animation that starts here and it goes in it only goes forward. But what if I have an animation where I can also go a little bit back and then go back forward again and go back again and go forward again and go backward again? Then in that case, I will need to know if I'm traveling in forward direction or in backward direction to be able to say if I have to add distance traveled from the last frame or I have to subtract it. So what I'm going to do for this is I'm going to say, I'm going to make another attribute here. So I'm going to say, maybe I can do this in this one, the same. Yes, I can do this in here. I'm going to say here, I'm going to copy the position on track here, this value. I'm going to copy this to all points. So I'm going to say f at my pos on track equals, and then I'm going to make a channel reference, and I'm going to do it this way. My pos on, now I'm going to say copy here, copy pos on track, and I'm going to do it like this. And now, because I made a channel reference to something that doesn't exist yet, I'm going to say, I'm going to push this button and it will create a spare parameter with this parameter here. And now I can say here, copy parameter, and here I can say base relative reference. So now these will always work. So what I'm actually doing here is my pos on track is actually a copy of this. But now in my solver here, I can use this, this value that I just created to check if I'm going in the forward direction or the backward direction. And to do this, what I'm going to do here is I am going to have a, over here, you're going to go down. I'm going to say if, and if what? If what? If something, then do this, and else do this. So, and if something, then do this. Voila. But what is the if? Well, the if is if my position on track from this frame is higher than my position on track from the previous frame, then I'm moving in a forward direction, right? But if it's the other way around, so if my pos on track is lower than my pos on track on the previous frame, then I should move backwards. So this is what I'm gonna try to accomplish here. So if it's a float, f at my pos on track is bigger than, and then we're gonna use the same sort of syntax we did here with this one. But here, instead of getting, oh, point, I'm missing a closing bracket here. So I'm using a point expression once again, and I'm going to get this from the first, from this input, so the previous frame, so it's actually the second input. So not distance traveled, but I want to have my distance traveled, but I want to have my pos on track. Oh, track here. So if my pos on track is bigger than my pos on track on the previous frame, then we're going to do this. Else, and now we're going to copy this, we're going to subtract it, because then the distance traveled should be lessened. So here we go. If I did not make any mistakes now, what is going to happen here is my distance traveled. Well, for now I've got only animation going forward, but let's say over here I would have had another keyframe, sorry, yes, and over here at frame 170 whatever, I would go back in time, let's say, or not back in time but back in space, sorry, here a keyframe. Then this one it goes up, well, first up, let's go up, go back and go forward. And now if we're going to check what this does with my distance traveled, it's going to say, okay, my distance traveled go up, still higher, up until a level where it's almost completely stopping. And now it should decrease. And yes, indeed, it's decreasing, as you can see. And now when I go back forward again, it's going to go increase again. Yes. So this is what I want. Yeehaw. All right. Now we're going to go to the real fun part. If you don't think this is fun yet, now we're going to get to the real fun part, is the rotation of all this stuff. So for this, I hope you paid attention in your math class back when you were in school, because we're going to use some stuff that you might have learned over there. First of all, what I want to know is the circumference, I think it's called in English, I'm not 100% sure there, but around the wheel. So if I have a radius of a wheel and I multiply that by 2 times pi, I get the circumference. I think it's the right word there. So I can put all this stuff in a wrangle again. So I'm going to use a point wrangle once more, and this point wrangle, what I'm going to do in here is first I'm going to declare internally, so I'm not going to make some attributes on my geometry, but I'm just going to use this for now on inside this wrangle. So what I'm going to say is float, and I'm going to call this circ, not from circus but circumference, equals 2 times pi. What is pi? $pi. Yeah, we can use it like this. And then we're going to use the wheel radius again. So I'm going to say right mouse on copy parameter times. And the thing is now, if I'm going to say this base relative reference for one reason or another, and I have no idea why this is not possible straight like this, it will replace it. So I cannot do anything about it. So what I'm going to do here to get it correct is, for example, this is the rotation, for example, that I want to use. So I'm going to say copy parameter, just for now say paste relative reference, and now the channel reference is correct, you see. And I'm going to delete this once more, I don't need it, but in here I don't need this string expression here. I do not know what this, I want just this. Now it gives me the value. So and that's the same as what I just copied. Look, voila. So what I'm going to do, once again, I'm going to make a float, and this float I'm going to call it circ, and I'm make it 2 times $pi times this point comma. Voila. Here we go. That's my first step. Then I'm gonna want to have I want to calculate. So this is a distance, right? So this is a measure of how many meters or centimeters or whatever it is there is around the wheel. So if I have the amount of distance that is traveled, and I divide that by the circumference of the wheel, I get how many times this should have rotated. And if you don't understand this, then just bear with me and you'll see that it will work. I'm going to call this an angle. It's a float angle that I'm going to make. And I'm going to call this, let me see, the distance traveled at distance traveled. That is a float, by the way, f at distance traveled. That's the one I want. Divided by circ. Right? But I still need to put some square. No, not here, sorry. I need this one. But this one, before I do this, I have to let's just let me see. I have to multiply this still with $pi and 2 once again. No, I have to use a magical here. 2 times $pi times this. That should be my angle. All right. I hope this is gonna not error. That's not gonna error. Okay. Space to make it readable. Voila. Okay. So to rotate a point in 3D space, the computer has a way of calculating things, and it's doing this in a way that is a little bit different than how we humans would like to see things rotate, because it will use, for example, a quaternion, which is called orient, and a quaternion is, well, not really readable for normal people. For there might be people that actually are able to read this, but I'm not one of those, and most people that I know don't know how to read normal quaternions and say, oh, this is how it's rotated. But the computer uses this. One of the reasons to prevent gimbal lock and things like that. If you want to know what that is, just Google it. But it's a way that the computer has to store rotational data and to make sure that it always works. But in order to make a good quaternion, we first have to be able to tell this quaternion that we have to rotate something around a certain axis with a certain amount. And how to rotate this, we're going to do this with a matrix. And for this, I'm going to make first, I'm going to make a matrix first. So, and it's a matrix 3 that I'm making. And if you don't know what this matrix 3 does, well, it's actually, well, it's more or less, I can show you a little bit. It's more or less the same as these things, these values: translation, rotation, and scaling. That's actually more or less what's going to be put into a matrix 3. Well, I have to finish this up because otherwise it's going to error. But I'm going to call this M for now. This is my matrix, and I'm going to declare this as follows. I'm going to declare this as the default values that we had previously with the orient along curve, because if you remember, we made an up vector. Let's see, we made an up vector, that's the purple one, and the normal vector is this one. So I'm going to use this up vector and this normal vector to make this first matrix that I'm going to use to orient or to rotate around. So this matrix M that I'm making here, I'm going to define it by make transform. So that's the transform that I'm going to use here, and that is defined by the normal, so at n, and by the up vector, so at up. Only small letters here, no capitals here. So bracket close, point, comma. So that's this one. All right. So now if I want to rotate something, then I can use the rotate function to rotate this matrix that I've got here around a certain angle, and around with a certain angle, sorry, and around a certain axis. But the axis that I have to rotate around, I have to declare this first. I could, of course, use my normal, because this is what I'm rotating around, right? I'm rotating around this yellow little axis here. So, but I'm going to do something even better than using the normal right away, because in order for orientations and rotations and everything to work perfectly fine, we have to normalize the normal first. And even though this normal is probably normalized already, I want to make 100% sure that it's normalized. And what does this mean, normalized? This means that the vector, the values of the vector in this normal stay between 0 and 1, or actually minus 1 and 1. So they don't exceed 1. So that's what I'm going to do here. I'm going to say vector. Oh, I'm going to say my own vector, and I'm going to call this axis. And this axis, I'm going to say this is a normalize here. Oh, not this one. Normalize this one. And then at and so I'm going to normalize my normal and store that in axis. So now that I've got my matrix, I can say rotate my matrix, and if I do this, I get some hints on how I can use this, and I'm actually going to use this one. Let me see here, matrix 3. So I'm going to rotate my matrix 3 by an amount over an axis. So what amount? That is angle. Oh, sorry, first, what am I going to rotate? I'm going to rotate my M, that's my matrix. Then how much do I rotate? Angle. And then around which axis? That's axis. That's the one we declared here. So bracket close, point comma. And now that we've rotated this matrix, now we can use this matrix to make an attribute which is called orient. And this orient, I'm going to declare this as an attribute for my geometry, and that is a quaternion, and a quaternion from this matrix, point comma. And now if I did not make any, oh, I have to put an is here. And now if I did not make any mistakes, I'm gonna have an orient over here. So it's 4 values here, and you see these values, I'm not able to say what these values will result in from orientation, but the computer will, fortunately. So now if I do this and I click over here, once this is animating, oh, where are we? Go back to frame 0. Oops, there we go. Let's see what's happening. I'm gonna rotate. Oops. Well, this is a little bit difficult to see, so what I'm gonna do is I'm gonna make the wheel radius a little bit bigger, so we can see better. And I'm gonna go here, and we're gonna, okay, so the wheels are rotating in the wrong direction. Well, this is not really a problem, because what we're gonna do, we're just gonna say minus for the angle, so it's rotating in this direction. Later on we'll see some more nice nifty tricks for this, and voila, now they are rotating in the right direction. And now I'm very curious to see at this position a little bit later on, where we were over here, where it went to stop. If I'm going back, oh, it automatically rotates back as well. Oh, how cool is this? And when we continue to go forward, it rotates in the right direction. Yeehaw! All right, so this is the meat and potatoes of this part. Actually, I think I'm going to stop this part now, because it's been long enough that you've been with me. You deserve a cup of coffee, and I do too. So I'm going to keep it at this. I'm going to save it out as part 4, I think. Yes, and then I'll see you in part 5 for how we're going to make multiple sets of wagons here. So file save as number 4. And I'm gonna stop the recording and I'm say, okay, enjoy your coffee.